Hello, my name is Tony DeLigio. I'm a senior editor with Plastics Technology Magazine, and I'd like to welcome you all to today's webinar, Reducing Mold Cycle Time with Moldflow. Our presenter today will be Joe Huegel. He is a technical specialist at Autodesk. Joe has a plastics engineering degree from Penn State University and has spent most of his professional career focusing on injection molding simulation using Moldflow. He is now a subject matter expert on the simulation team at Autodesk, and prior to Autodesk, his work experience included time with Beaumont Technologies and Trucklight. Joe currently lives in Erie, Pennsylvania. A couple of quick notes before we start. A recording of today's presentation will be posted to PT Online, the Plastics Technology website, and all attendees will be sent a link via email. Also, you can enter questions at any time using the webinar interface. All right, with that, I'm going to kick it over to Joe, and we'll get started. Joe?
Excellent. Yeah, thank you. So I want to thank everyone for joining the webinar today. I'll be presenting on the topic, how to reduce mold cycle time with Moldflow. I want to start today by providing an overview of what I'll be discussing throughout the presentation today. First, I'm going to provide a quick overview of the Autodesk simulation portfolio, then dive into the Moldflow product and talk specifically around ways to use Moldflow to evaluate cooling. I'll talk about the methods to reduce cycle time and how Moldflow can be used to help in these 5 areas related to part design, traditional or conformal cooling, mold material selection, and machine process parameters. We'll end with a quick summary and then a question and answer session, as noted before, where you can type any questions into the chat section of the webinar. So before I start talking about cooling and reducing cycle times, I thought it'd be relevant to highlight the Autodesk simulation portfolio to give the audience a grasp on the broad range of tools that are designed and developed to provide complete engineering solutions. Autodesk Nastran and Nastran InCAD are used for linear and nonlinear structural FEA to simulate how parts and assemblies perform under specific loading, impact, vibration, drop testing, or fatigue. Autodesk CFD, or for computational fluid dynamics, is used to evaluate gas, fluid, or airflow in a system. For example, you can simulate how an electronic circuit board will heat up and how the cooling system needs to be designed to properly maintain an acceptable operating temperature. Another example would be fluid flow through a pump or a channel. Our Moldflow software leverages the CFD meshing and solver to simulate complex cooling channels in a plastic injection mold, which I'll discuss a little bit later. Autodesk Helios PFA is designed specifically to improve accuracy, efficiency, and convergence for nonlinear simulation of advanced materials. Helios PFA also provides the ability to leverage as-manufactured material properties from Moldflow to include the impact of fiber orientation, nonlinear material behavior, and weld line strength calculations in a structural analysis. Autodesk has also invested in simulation tools for the additive manufacturing process as part of the Autodesk NetFab product line. I'll share more on this tool a little bit later in the presentation also. And finally, Moldflow, where most of the remainder of this webinar will be focused, is used to simulate the plastic injection molding and compression molding processes. The Autodesk simulation team builds and develops our products with a specific purpose in mind. I'll demonstrate in this webinar how our Moldflow portfolio has tools and workflows that can be specific for designers, engineers, and analysts, depending on the stage of the product development process. I will also highlight the broad range of processes that Moldflow can cover and provide detailed insight in order to help throughout the development process. I also plan to show examples of how Moldflow can be leveraged as an upfront analysis tool and highlight functionality that uses optimization and design of experiments to drive the design of a plastic part. For those of you not familiar with our Moldflow tool, Autodesk Moldflow provides a complete set of injection molding simulation tools that allow you to predict and help correct part defects to avoid costly production delays. It's also used to simulate the most advanced molding processes in use today. It can provide the highest degree of confidence in simulation results for even the most complex geometry and uses the world's largest plastic database of its kind, with over 9,500 materials characterized for injection molding simulation. In short, Moldflow gives you the tools you need to overcome the challenges of developing injection molded parts. So as advertised, this webinar will talk about the importance of cooling and what are the main factors that drive cycle times. When we talk about the importance that cooling plays relative to injection molding, there are two main factors that cooling affects that everyone is concerned with: quality and cost. Cooling has a significant impact on the part quality, affecting everything from surface finish, residual stress, and crystallinity. Cooling also plays a significant role in the overall shrinkage and warpage of the part, which affects the ability to control dimensions within a specific tolerance. Cooling time also affects the production and part cost. Typically, the cooling phase of an injection molding process makes up the majority of the cycle. And since time is so critical to production and part cost, reducing the cycle time on a part can equal significant savings. The cycle time can also influence the decisions on the number of cavities that are required in a mold to meet specific production requirements. Understanding how important cooling is to the injection molding process, a question for the audience is, are you running optimized cooling in your molds? And how would you even know? So this is where injection molding simulation is instrumental to evaluate cooling in your mold. Moldflow is used at every phase of the development process to make engineering decisions, from basic part-only estimations of cycle times to comparing different cooling circuits and mold materials, to even evaluating other approaches such as conformal cooling or rapid heating and cooling cycles. As mentioned before, I'm going to focus on these 5 areas to show examples of how simulation is used to predict and reduce cycle times. First topic is related to plastic part design and how this critical step in the product development process factors into the overall cycle time. It's estimated that 75 to 80% of the final manufactured part cost is determined in the design phase. The part designer has a lot of decisions to make during this process. Not only do they have to engineer the part to make sure it meets the form, fit, and function requirements, they also need to consider the impact of manufacturability. Decisions such as material selection, part thickness, and how they design features can drastically impact cycle times. Simulation can help with some of these difficult decisions. For example, can the part be filled with a selected material? What about alternate materials? What happens if I make the part thinner? Can I still fill the part with the pressure limitations? And will the part still meet structural requirements? Based on my experience, I feel that simulation is not run early enough during the product design stage to use to answer these questions. But when simulation is run at this stage of the development process, changes to the part design can easily be made and can be made before things get expensive. Moldflow has recently added tools and features into the software that can help specifically with evaluating the impact wall thickness has on cycle time, as well as other quality criteria. Moldflow allows the user to modify CAD surfaces inside the software, then leverage those geometry modifications as a variable in a parametric study. A parametric study can investigate multiple variations of wall thickness change, for example. The analysis allows you to specify quality criteria such as the time to reach ejection temperature to understand the impact on cycle time. To add even more information and value, the analysis will also show how changing wall thickness impacts other critical results like the pressure required to fill, sink mark depth and locations, or even shrink and warpage predictions, just to make sure the part can still meet the flatness and critical dimension tolerances. Let's take a look at a simple example that compares the predicted time to reach ejection temperature for 3 different wall thicknesses. The image on the left shows the part with a thickness of 3 millimeters will require just over 26 seconds to reach the specified ejection temperature. When the wall thickness is reduced to 2 millimeters, The analysis shows the time to reach ejection temperature is almost cut in half at 13.7 seconds. And the final image on the right shows a part thickness of 1.5 millimeters requires just over 8 seconds to reach that same target ejection temperature. I find myself asking plastic part designers how they determine what thickness a part should be, and the common answer I get is, well, the last part that was designed had the same wall thickness and that seemed to work, so they went with it. So the illustration here, really what it shows is some drastic thickness changes. But what if we consider smaller changes? What could that have as far as impacting a cycle time? What could that mean for production? I'm going to shift gears a little bit and talk about some of the aspects related to mold design that impact cycle time. First, I'm going to talk about rules for traditional cooling lines. There are a number of guidelines to aid in designing an efficient cooling circuit with regards to cooling line placement, diameter, and spacing. Moldflow can take these guidelines to the next level by simulating the efficiency of the cooling circuit and can identify hotspots in areas in the mold that will limit the cycle time. Design variations can be virtually tested in Moldflow to determine the impact that changing the cooling layout or adding baffles and bubblers, for example, to critical areas. Moldflow also uses the thermal profile from the cooling analysis to determine the impact on shrink and warp. Using this hedge trimmer example, I wanted to show how using Moldflow during the mold design phase can be used to make decisions. The original cooling design, shown here, was intended to provide initial mold temperature results, so the mold designer was aware of the local hotspots and what impact they may have on the cycle time and part quality. From the result, you can easily visualize the large temperature variation and the hotspots that will cause cycle time limitations, as well as shrinkage variations. From here, the mold designer can use this information to address the specific problem areas. The next design variation uses a combination of baffles and a mold insert with a higher thermal conductivity to help pull out the heat in that local hot area. The resultant simulation shows a smaller mold temperature range and predicts a shorter overall cycle time, but still shows areas where the cooling design can be further improved. These design iterations can be continued until a target cycle time or mold temperature profile is reached. A quick comparison shows the temperature variation across the mold surface of the original design is 51 degrees Celsius, whereas the revised design reduced the temperature variation to just over 38 degrees Celsius. This brought the average temperature close to the target of 50 degrees C. There are multiple ways to view the cycle time results. This result indicates the overall time to reach ejection temperature, as well as shows each specific area and how long those areas require to reach that temperature. The plots here are shown at the same point in the cycle, around 40 seconds, and we can easily visualize the amount of material that is still above the ejection temperature. The highlighted area, which was identified as a cycle time limitation from the original design, was specifically targeted with the cooling circuit changes. I want to share another specific customer case study. So this example is from a company called Huegel. And the specific part here we're showing is a pond filter housing. They approached the redesign to this part using Moldflow to attempt to minimize their production costs. But through their optimization studies, they were able to reduce the cycle time by 2.2 seconds by making a small change to their cooling circuit. They didn't stop there. They were able to reduce the wall thickness and use Moldflow to predict the ability to still mold the part under the injection pressure limitations. This change not only saved on material costs, but it also reduced the cycle time by 7.3 seconds. These combined design changes resulted in a 26% savings in production costs. So what I like specifically about this success story is that the company used Moldflow to identify areas of the mold and part that limited the cycle time and made adjustments to both the part geometry and the cooling circuit. So the next approach I'm going to discuss as a method to reduce cycle time is conformal cooling. But conformal cooling, by definition, is a cooling channel passageway which follows the shape or profile of the mold or cavity to provide uniform cooling. These cooling channels are impossible to machine using traditional gun drilling and require growing these mold inserts by metal additive manufacturing. As the metal additive manufacturing process continues to gain momentum in the industry, the need for an easy-to-use and accurate simulation tool is critical for the design and justification of using this method in a mold. Because this approach is one of the best ways to achieve uniform cooling, there are many benefits that can be reaped, such as reducing warpage and minimizing cycle time. Inserts created by additive manufacturing are typically more expensive than a traditional insert, and concerns of durability and maintenance are also issues. Leveraging Moldflow as a simulation tool is a great way to help when justifying the insert cost versus the expected cycle time savings. Moldflow can also show the additional part quality benefits, like the reduction in shear stress or warpage. So as I mentioned before, Moldflow has a specific way to solve the coolant flow and heat transfer calculations by leveraging the Autodesk CFD meshing and software. It's important to understand that coolant flow through non-traditional channels is a complex problem, which really requires a more sophisticated calculation method than the traditional pipe flow calculations. This is why Moldflow leverages the proven Autodesk CFD meshing and solving technology directly inside the Moldflow interface. This is critical to ensure the intended design can deliver the expected results. So historically, what we have seen is these unique conformal cooling channels were designed and simulated using a standalone CFD tool to validate coolant flow rates, turbulence, and pressure drop through the circuit. What was missed is the impact the cooling circuit has on the mold temperatures and ultimately how the part will shrink and warp with the conformal channels. Moldflow now allows this connection to fully explore the advantages conformal cooling can provide. Again, I'm going to highlight another case study where we compare a conformal cooling circuit to a simple conventional circuit. So due to the scale of the small features of this part, traditional cooling was unable to direct cooling lines or baffles into these small areas. The analysis here will compare each cooling design and the resultant time to reach a specified ejection temperature. Comparing these results side by side, we can clearly see the differences in temperature and predicted cycle times. Conformal cooling design predicted a maximum mold temperature of 139 degrees Celsius, which was 35 degrees Celsius lower than the conventional design. This translates to an 8.3 second cycle time compared to 12.5 seconds. When evaluating the impact on production volume, you will notice the conformal design can run 145 more parts per hour using a single cavity mold. This is the type of information that can be used to help justify using a cooling approach. Another benefit to weigh here could be the number of cavities or molds needed to meet production volumes. Being able to produce 145 more parts per hour could allow for a lower cavitation mold, which could create a smaller mold footprint that can be run in a smaller or lower tonnage press. Another specific measurable benefit of using conformal cooling in this case study is the reduction in warpage or deflection. The conventional design showed hotter mold surface temperatures in the pockets of the part. This differential cooling effect led to more shrinkage on the inside of the part, which creates the box effect we are seeing here. The warpage reduction along with cycle time improvement makes a compelling justification for the use of the conformal cooling insert. As I briefly mentioned before in the simulation overview, Autodesk NetFab includes a process simulation tool which is used to predict the net shape of a product produced by the metal additive manufacturing process. I felt it was relevant to share this technology when discussing the conformal cooling option for this webinar, since Autodesk has not only recognized the need to simulate the effect conformal cooling channels have on an injection mold, but we've also recognized the future demand to be able to simulate the build process of the additive metal inserts. There are a number of reasons to simulate the metal additive process. One of the main reasons being the additive process often requires multiple iterations to produce the desired shape of the final product. During the additive process, significant amounts of energy and heat is required to sinter the metal powder, which creates stress and deformation of the metal product. Using the Autodesk NetFab process simulation tool can be used to predict the final shape of a part, and that can drastically help reduce the iterations required to produce a part in tolerance. There are a number of additional features that go along with the ability to predict the deformed shape of a part produced using additive manufacturing. Predicting support failures, recoder interference, and the ability to automatically create a compensated preform geometry are just a few ways that Autodesk NetFab can significantly reduce the number of design and production iterations for this additive process. Getting back into the cooling topics, the next section I'm going to talk about is how Moldflow can be used to evaluate the performance of different mold materials relative to cycle time and durability. Mold or tooling engineers are given the difficult task to make a 3D part model and build a mold that will produce the part within the given tolerances. So deciding where to locate cooling lines or what type of cooling circuit to use is just one aspect. Mapping out a cooling circuit can be difficult when you take into account all the components of a mold, such as ejection, slides, or lifters, and of course the runner geometry. Selecting the proper mold material for the best performance is another great area where simulation can play a critical part of the design process. Within Moldflow, the user can specify the mold material type they plan on using and evaluate the impact on these critical results. Moldflow makes it easy to compare the impact different mold materials will have on the overall performance. This image shows the mold temperature difference on the core insert between a P20 tool steel and a beryllium copper alloy. As we'd expect, the beryllium copper alloy does a better job at removing the heat from the highlighted areas, which happens to be a thin section of the steel that, due to ejection requirements and the physical size of the features, direct cooling lines were not able to be designed close enough to that area. The first analysis identified the hotspot and the cycle time limitation, which led to the designer to explore different mold materials with higher thermal conductivity. The more uniform mold temperature will provide less shrinkage differentials and lower cycle times. But how much lower is a critical question that Moldflow can help us answer in order to justify the additional cost of using the beryllium copper alloy. So we're able to see here inside of the Moldflow software the estimated cycle time for the beryllium copper alloy is 7.3 seconds shorter than the P20 option. Cycle time being one direct measurable, but part quality can also be used to help make this decision. Typically, it's more difficult to prove without simulation though. So reviewing the same part again, we can compare the impact mold material has on the predicted warpage result. These plots highlight the warpage in the critical area along the back surface of the part. The part with the P20 mold steel insert shows more deflection along this edge. The original simulation on this part identified this warpage issue is primarily caused by differential cooling, meaning the temperature difference from the core side to the cavity side created shrinkage differences, causing the back wall to bow in towards the center of the part. In order to address this issue, the temperature variation between the cavity and core had to be minimized, and this could only be reasonably accomplished by changing to a higher thermally conductive mold material. Selecting mold materials have other considerations to take into account, other than just impact on cycle time. Material performance also needs to be considered. For example, mold deflection and fatigue can eliminate the possibility to use some materials depending on the strength and modulus of these materials. Core deflection and thermally induced stresses also need to be considered to make sure that there are no premature failures of the mold inserts. Moldflow can help predict these issues whether directly inside of Moldflow or by leveraging the Moldflow results to drive boundary conditions in a structural simulation tool like our Autodesk Navstran. The last topic on reducing cycle times I want to cover today is related to the processing variables we have on injection molding machines. As you'd expect, increasing or decreasing the melt temperature of a material will impact how long it takes for a part to cool. Likewise, if we increase or decrease the water inlet temperature from a thermolator, this will impact the overall cycle time. The difficult part here is how to measure or quantify these changes, and also how changing the process conditions affect other criteria, such as injection pressure, volumetric shrinkage, and warpage. Typically, simulations in Moldflow are run at one set of process conditions. Then one or two settings might be tweaked to understand how fill rate or pack pressure, for example, might affect certain results. The Design of Experiments tool is intended to disrupt that behavior and allow the Moldflow user to easily investigate multiple variables and their impact on the most critical results. We recognize that setting up a Design of Experiments analysis needed to be simple, and there needed to be a simple way to review the large amount of data in order for it to be useful. In order to explore the wide range of process conditions and drive optimization, the DOE setup allows the Moldflow user to select which process conditions to vary. All of the processing controls available in Moldflow, such as melt temperature, water inlet temperatures, filling controls, pack pressures, and times, can be used as part of the DOE. I also discussed earlier how thickness variations and geometry modifications can be used in these optimization studies. From there, the user specifies which quality criteria are most important to the part. Results like cycle time or time to reach ejection temperature. Other results like sink marks, clamp force, and critical dimensions for warpage can also be specified to understand how these variables impact each quality criteria. Performing a Design of Experiments virtually versus on the actual molding machine can save significant amounts of time and money. And the information gained from these results can be beneficial when going through initial mold trials and process optimizations. These DOE results can be plotted on a 3D surface response plot to show the combined impact of changing variables. In this case, melt temperature is on the x-axis and mold temperature is on the y-axis. The plot on the left shows warpage, and the plot on the right shows the time to reach ejection temperature on the respective z-axis. As you'd expect, the lowest mold and melt temperature represents the shortest time to reach ejection temperature. But those same settings actually represent the highest warpage magnitude. The warpage plot also shows that deflection is more sensitive to melt temperature changes than to mold temperature changes, since the slope is steeper for the melt temperature axis. This information can be used by a process engineer before running additional molding trials or capability studies to identify the dominant factors and what variables can influence a specific part response. There are also other ways to evaluate specific DOE results. For example, this animation plot provides all of the input variables on a sliding scale to allow the user to adjust variables and immediately evaluate the response. Here we can easily see what happens to the deflection of the part when melt temperatures increase or decrease, and the same for mold temperature. This is also important to illustrate the overall warpage trend to determine if changing one variable can actually reverse or impact the warpage trend. These plots can also be created to understand the impact on other results related to part quality. For example, volumetric shrinkage. Again, we can see how changing the mold and melt temperatures impact the volumetric shrinkage, which can be correlated to overall part size and also by locating where sink marks may occur. So to summarize, I explained the importance that cooling plays in order to produce high-quality parts while still earning a profit. I also showed how Moldflow can be used at each stage of the development process to make sure you can answer yes the next time you're asked the question, are you running optimized cooling in your molds? Thanks everyone for your time today. We'll now open up the chat for any questions. I also listed my contact information if you have any questions, you want to reach out directly to me. Thank you.
Great, thanks, Joe. Well, again, if y'all have any questions, feel free to type those into the webinar interface, and we can go through those. We've got a couple already, so I'll jump right in. The first one was regarding material property temperature. What material property temperature is used as the ejection temperature? I don't know, I guess that's maybe trying to account for what you have to run the material at, and then how that relates to the part cooling enough to be ejected. Or maybe if you can speak a little to, you mentioned the materials database and how Moldflow kind of accounts for what material is being used.
Yeah, so anytime we characterize a material, there's a handful of tests that we like to perform to make sure the material can be run in simulation. So specifically to the ejection temperature, we run a DSC scan on the material, and we use the TG endpoint to specify the ejection temperature.
Okay, gotcha. Next one, how does the software represent mold components? Do you have to model them in Moldflow?
Yeah, so for this, specifically to answer that question, there's a handful of ways that Moldflow can use different geometry. So whether you're using a design from part only and you want to build your mold inserts in Moldflow, we have the ability to do that. We also have the ability to import your entire mold assembly if you would like to, or you can just select specific components or specific inserts that maybe are made from a different mold material to import and represent at that mold material. So I guess to answer the question, we have the ability to model components inside the software as well as import 3D geometry from a mold design.
Okay. With regards to the actual product being used, I guess, in cooling, can Moldflow simulate the use of oil in channels or heater cartridges to get the mold temperature results?
Yeah, so I didn't focus on those components today, but yeah, we absolutely have the ability, whether it's with high temperature thermoplastics, we can simulate oil flow through the channels, or heater cartridges. We can model those as different components, as well as if you were running a thermoset material or like an LSR or a rubber that you had to heat the mold. We can also use heater elements to drive our mold calculations, mold temperature calculations as well. We also simulate rapid heating and cooling cycles. So if you're doing a high pressure steam, then an air purge, and then cold water, we can simulate that, as well as using induction coils for induction heating and cooling.
Okay. I had a question here regarding whether you could do Moldflow with an existing mold. I guess maybe this would be a tool that's been built, and would you guys just go ahead and enter in that existing CAD data, or this isn't strictly tools that are in the design phase, I guess?
Yeah, so kind of how I answered the question previously, if you have a full mold design or you've got a mold that's already in production and you're trying to do maybe a baseline analysis to determine what areas of the part might be limiting cycle times, for example, we're able to simulate your existing mold design and ideally your material and process conditions to come up with a baseline to say when we make changes, whether it's material or process or mold geometry related, we can quantify how much of an impact those changes have. So absolutely. Okay,
great. And with regards to, you talked a little bit about NetFab and conformal cooling. I guess it's early days yet, but what are some of the things you guys have picked up on in terms of, with the traditional cooling channel, you're looking for that turbulent flow. Are you able to kind of get a feel for, in these kind of non-conventional cooling channels, what the flow is going to be like down to that, or what have you seen from the early portions of that particular part of simulation?
Yeah, so the customers that are using specifically conformal channels, when they're not traditional diameters, maybe they're odd shapes, for example, and maybe ovalized, we do calculate the velocity through those channels, and we calculate like a temperature rise as well as pressure drop. So from that, we can essentially calculate the effective diameter, velocity, and be able to calculate our Reynolds number from those values.
Okay, no, definitely. And with regards to, I mean, obviously there's a lot of variables you could play with. Are you able to, and we talked a little bit about materials, but are you able to say, in addition to maybe tweaking the wall thickness, that if you used a different material that would potentially, run at a lower temperature, that the impact that would have on the design and on the cycle time? Or can you talk a little bit about how much you're able to play with, the material that you've chosen to run the simulation on?
Yeah, so from our material database, there's, as I mentioned before, there's close to 10,000 different thermoplastics, and with each material that's characterized, we test for things like specific heat and thermal conductivity, as well as things like rheology and everything. But when we change a material, we can also look at if that material is going to have a better performance with lower injection pressure or faster cooling rates. We can certainly compare those side by side. We don't have anything set up specifically right now in our design of experiments to vary materials, but that's certainly something that we're looking to do.
Okay. And maybe to kind of touch on that design of experiment and the concept you talked about, if you could expand on that, where folks would be able to do a virtual DOE versus going through the steps of an actual design of experiment. What have you seen there? And obviously you've probably seen some folks with some success doing that.
Yeah, so one of the things that I've seen is we're definitely not going to replace the fact that you're going out to do some capability studies on your molding machine. What the intent of the design of experiments in Moldflow is to really look at a wide range of variables and really understand how those impact specific quality criteria. So when you do get to the molding floor, you can have a more focused approach on, for example, if you're trying to get a part to be in tolerance for maybe flatness, for example, and you ran a virtual DOE using Moldflow, we can really recognize what factors are going to influence that flatness. So, for example, if melt temperature has very little impact on it, we don't have to waste our time on the machine varying the melt temperature. If we know packing pressure has a huge impact, that's probably where we focus on first. So it's really arming the process engineer or the entire team with information of how to go and attack a capability study or initial mold startup. And certainly trying to get you the information so when you get to your first molding trials, you have a process window that you're fairly confident that you'll be able to mold acceptable parts with.
Okay, no, definitely. It's a very powerful tool. Well, I'm looking at the questions. It looks like we got through the ones that had come in, and I haven't seen any more come in. So I think at this point we can wrap up. Joe, I'd really like to thank you for the great presentation and your time today, and thank Autodesk for supporting the webinar. And I'd like to remind all our attendees that we will be sending the link to the full presentation if you wanted to go through anything else with that. And also remind you to check PT Online for future webinars that may be of interest to you. So thanks again, Joe, and thanks to all our attendees, and hopefully we will be chatting with you again in the near future.
All right, thank you. Thanks, everyone.